All right. Hello, folks. Welcome to today's webinar. We'll get started here shortly. Um, let's just get a few things set up. So for today's session, just a few housekeeping items I'll mention before we jump into it. Today's session will be recorded and available as a playback. So for those who if you have colleagues who maybe weren't able to make it or you wanted to share this with them after the fact, this will be available. Also, I will mention at the end of today's session, we will go into a formalized Q&A. So if you did have any questions, please feel free to make use of the chat box feature, typing any questions in, whether it's related to the content presented on screen or just any general questions you have, maybe as it relates to work that you're doing. Definitely feel free to type those in and stick around at the end of the formal session and we'll go through those together. All right, but let's go right into it here. So today our webinar focused on dynamic mechanical analysis, DMA theory and applications. My name is Arya Hakimian. I'll be just setting us up a little bit of an intro and kind of taking care of some of the logistics in today's talk. My colleague, Arya Shadostambik, will actually be the main feature here today. He's going to be taking us through the bulk of today's session. And we also have a special guest, Hugh Baudrier, visiting us in town at our facility. He's the material testing international sales manager at Metrovib. So Hughes will be joining us for the Q&A session at the end. So again, definitely feel free to make use of these two great resources if you did have any DMA specific questions you'd like to ask. But all that being said, we'll jump in. I'm going to start it with just a little bit of a brief introduction to C-Therm. For those who may be new to us, essentially C-Therm Technologies, really, we are focused on thermal conductivity. We develop various methods that are transient based. And while it won't be the focus of today's talk in particular, did want to kind of go over a little bit of what our offering is. Because again, if maybe you're interested in multiple material properties, whether that's conductivity, mechanical properties, certainly able to help out with that. So from a thermal conductivity perspective, I just wanted to introduce Trident. Trident is a instrument platform which offers multiple methods for thermal conductivity characterization. I will flag that if you are interested in thermal conductivity as well, we do have a vast array of resources available on our website. So definitely feel free to make use of those. We have a wide variety of tech resources available as well. So again, won't be the focus of today's chat, but if you did have any questions, we'd be certainly happy to answer those. And the idea behind Trident really stems from this quote here, famous quote from Abraham Maslow: "When all you have is a hammer, everything looks like a nail." The idea behind Trident being modular in nature, you can really pick and choose the best tool for the task at hand. One of the biggest sources of poor data that we see out there is when you take a really good method, but apply it in a scenario or in a sample that just really wasn't designed for. So, ultimately with the flexibility of the Trident system, you can really pick the best option for your specific goal without having to compromise based on just what you happen to have available. So, we do have a free resource available on our website for thermal conductivity. This is a method selection guide, really goes over a lot of the background on the methods that are available out there, as well as what we offer here at C-Therm. If you are interested, it's a free resource. Definitely feel free to take a look to learn a little bit more. Now, I will mention, so I said C-Therm, we focus primarily on thermal conductivity. That's really our core, but we are partnered with various groups. Of course, today, the focus on Metrovib, DMA product line. This will be featured heavily in today's session. We also work with a company called Rigaku for their thermal analysis product line in North America. So different DSC, STA, and TMA characterization. So again, if there's any interest in some of these other properties, these are different areas that we could certainly help out with. We also have a full service test lab, TAL, Thermal Analysis Labs. They offer all of the instruments that we have in our main product portfolio, as well as others for contract testing. So maybe if you're not ready to necessarily make a jump to an instrument purchase, but you do need to get some materials tested, again, various resources we have available to help those different needs. So if you'd like to learn more about any of the product lines, whether it's conductivity, the Rigaku, or the Metrovib systems, we're certainly happy to do more of a one-on-one discussion with you. We can schedule a technical consultation, learn really more about what your interest and your focus is on. You can see a live demonstration of these instruments applied on a material that's representative of your application. So if that was of interest, definitely feel free, again, just reach out to us in the chat box or send us an email. We'd love to get one of those set up with you. And also, if you're interested in getting some pricing information, certainly happy to provide a quote. So we'll end here just with the intro, just a client testimonial. We always like to, really talk about what our folks are saying about us, different groups that we've worked with. This is from Tavsud. They're a Trident user, kind of noting that they're using the thermal conductivity testing for their process safety studies. And related contract testing has provided their lab with invaluable new capabilities. So if you're interested in kind of seeing what other groups are saying, we do have a testimonials page available on our website. Definitely feel free to take a look at that. That brings me to the end of kind of, just setting the stage, a little bit of background about C-Therm and what we do. At this point, we'll jump into the main session, again, titled Dynamic Mechanical Analysis, DMA Theory and Applications. And I will throw it over to my colleague, Arya, to take us through this portion of the talk.
Okay, hello everyone. Thank you so much for joining us today here at C-Therm Technology. I'm Arya, lab technologist, and I'm going to walk you through a quick webinar on the theory and application of dynamic mechanical analysis. I'm going to share my screen here. Ready? Okay. I apologize okay. So, dynamic mechanical analysis, or DMA, theory and application. So before I start and go through the content, we are a proud partner and distributor of DMA Metrovib products, high performance DMA mechanical analyzer, for highly rigid and one-piece test frame. They provide accurate low strain measurements as well as high force for stiffer material. We can use large specimens for your testing, and their capability is not limited to only specific deformation mode. And as I mentioned before, you have freedom to test your samples from a wide range of materials, soft and stiff, to a wide range of different conditions like frequency and temperature. Metrovib product range, you can see on the left side, we have low force DMA DMA 25, DMA 50, as well as DMA Plus series, which is our extraordinary series of DMA with high force capability, 300 plus 1,000 and plus 2,000 for testing all sort of materials with different stiffness. And on the right-hand side, you see high-frequency testing machine, VHF 104, which can experimentally test materials with a frequency up to 10,000 hertz. So going back to our introductory slides, so today I'm going to talk about theory a little bit. Previously, we had another webinar on different applications of dynamic mechanical analysis for polymer composites. Today, it is going to be more about theory. So let's just talk about dynamic mechanical analysis and what is the this testing method. So dynamic mechanical analysis, or DMA, is a powerful tool to measure the viscoelastic properties of the materials, including filled and unfilled polymers, rubbers, and other soft materials. Viscoelasticity is the property of both viscous and elastic characteristics when undergoing a deformation, which is the basis of DMA test. So here, there are important words that we should pay attention to while talking about viscoelastic properties and DMA measurement. So as you can see, viscoelastic is a big portion of this testing and the subject that we're going to be talking about. And viscoelasticity basically has two parts, as it explains itself: a viscous and elastic portion of the material. I'm going to elaborate more on that shortly. And the important part here is that viscoelastic properties are not limited, but unique to dynamic mechanical analyzers. And that's the most promising way of testing these properties and the fastest. So talking about viscous and elastic. So let's first understand what it means when we say viscoelasticity, and let's talk about the backbone structure of this word, which is viscous and elastic. So elasticity simply means is the tendency of a body to return to its original shape after it has been stretched or compressed or by any means deformed. So a very good example of that will be spring. When you stretch it, when you hang a mass from the bottom, so it moves as the force is applied. And on the other side of the spectrum, we have viscous or viscosity, which is the physical property implying a dependency between stress and strain rate. So by applying different stress rate or strain rate, you get different response and different properties of your material. And a very good example of that will be dampers. So moving forward, I am going to talk about more of the structure explanation for the viscoelasticity, and to really understand what's going on behind all of these properties and this viscoelasticity when you apply a force or deformation. So on the left-hand side, you see a polymer chain. And as you can see, there's no stretch or any force by any means or any deformation applied to the polymer chain. So you can see its original shape. And in the middle part, you are applying stretch or stress as the means of deformation. And on the right-hand side, you can see the relaxation. So starting from the middle part, as you can see, because of that stretch and that stress applying in the form of tension, the molecule chains of the polymer start to aligning to the direction of the force that you are applying. And after releasing that force, you see that the chains are trying to go back to its original position. However, this is very important to be aware that there is a relaxation time going on here. So what does actually mean? What does that actually mean? It means after you release the force or deformation, your material does go back to its original shape, but not instantly. So there is a specific amount of time it takes for your material, which is called relaxation, to go back to its exact original shape. So at the short time or high frequencies, the response is solid-like, and at long times or low frequencies, the response is more liquid-like. So please keep these 2 points in mind. I'm going to explain more in detail about these 2 sentences, but keep that in mind that the response depends on the loading history. So up to now we understood what a relaxation means. So by understanding the relaxation, you see that by applying a certain stress, there is a deformation or strain followed by applying your force. And so I was talking about relaxation time and the time that your sample takes to go back to the exact original shape. That amount of time that you have to wait or your material relaxes shows itself in this stress strain graph by a phase angle. So there's a certain delay for your material to show that deformation after undergoing certain force. So the phase angle or delta or phase shift between the deformation and response is observed due to the viscoelasticity. So another, just a quick flashback to the viscoelastic property of the material. So one part of your material wants to instantly go back to the original shape like a spring, but the other part of your material does not want to do that. It wants to resist against deformation like viscous material. So that situation causes a phase angle between the stress and strain applied on your sample. Or in simple terms, after you're applying your force, the deformation that is followed by the force is not instantly happening. There is a certain amount of time and delay between the response and the force that is being applied. So talking about those 2 sentences about the effective frequency of your material, short times and long times, I mentioned that the response depends on the loading history, which can be frequency. So what is happening behind that is that the relaxation time that you can see, if you apply force, let's say stretching your sample quickly with higher frequencies, your materials stays on the stretch chain of the polymer. Let's say your material is a polymer, and it doesn't get a chance to go back to its elastic shape or original shape. And that causes your material to show higher stiffness properties. So again, by applying higher frequencies, higher deformation, your materials become stiffer and it kind of behaves like a stiffer material. On the other hand, though, by applying lower frequencies, you're providing enough time for your material to go through the relaxation time and it behaves less stiffer. So these are very important parts talking about DMA tests. 90% of the time you're dealing with frequency or temperature. I will go through temperature shortly, but understanding the frequency effect is very important. So by deforming your sample at a certain frequency, you will have 2 different components. So viscoelastic properties of the material can be illustrated using this image here. Imagine you're dropping a ball. So definitely after you drop the ball, it starts bouncing back up. However, it does not go back to its original spot that you released the ball. So this is a very good illustration to show 2 important components of viscoelastic properties. So the amount of energy that is being saved in your material, is being stored in your material, is called storage modulus, or that's exactly the elastic part of the viscoelastic property, which actually makes your material to tend to go back to its original shape. So it stores that energy inside of the ball so the material can go and bounce back up. But we 100% know that the ball will not go back to its original spot and location. And that amount of like the loss in height you can see is called loss modulus, which is related to viscous component of your viscoelastic property. So it's basically the energy that has been dissipated through the matrix of your material, and it's transferred through heat, and you don't see any response or return from that energy. So the elastic component of your viscoelastic property is called storage modulus. And the other part is loss modulus, which is an engineering part. So now let's talk more deeply about storage modulus and loss modulus. So what happens when you drop a ball? You have two components, as I mentioned, storage modulus and loss modulus. Storage modulus is shown by E prime, and the loss modulus is shown by E double prime. And so if you add these two components together, you will get complex modulus, or in a simple term, is how resistive is your material to any deformation. And as you can see on the right-hand side again, after applying a force or displacement, the other part is being recorded, there is a certain delay in that response. So the complex modulus is composed of E double prime or loss modulus and E prime or storage modulus. So now that we developed an understanding of viscoelastic properties of the material, let's see how DMA works and how actually DMA can measure these properties. So let's go through DMA principle. DMA, or dynamic mechanical analysis, is the most accurate technique for measuring the viscoelastic properties of the materials. DMA consists of applying a dynamic force, as you can see in the image, dynamic force excitation to a specimen of material, measuring the applied force and the resulting deformation. It's important to mention that dynamic mechanical analysis is different than static test. For example, like a tensile test, it's way different than DMA. And as you can see in the picture, there's a force applying in a dynamic manner. So unlike static tests where constant load is applied, a dynamic periodic load is applied. And the viscoelastic materials will have a phase angle between the force and displacements. And that's a setup for metric DMA. As you can see, there's a sample. This deformation mode is tension mode. I'm going to talk more in detail about the different modes of deformation of your sample. But this is tension mode. So as you can see, you mount your sample in your sample holders, and the bottom part starts deforming your sample in a dynamic periodic load, and there's a force transducer and displacement transducer that records the data. So now let's talk about various deformation or excitation modes. So DMA deforms your sample in vertical dynamic excitation, and it can be occurred in different ways: tension mode, compression, shear, and bending. So this makes, using different excitation mode makes DMA a very flexible analysis technique to address a large variety of materials, including thermoplastic polymers, thermosetting polymers, rubbers, metals, even ceramics, films, pastes, and even liquids. So it's a very versatile instrument that it can test different specimen with different properties and measure viscoelastic properties of your samples for different applications. So for a better illustration of different modulus or different deformation, we can see on the left-hand side, you have Young's modulus. So this modulus is for elasticity. And so it's basically for stretching or compressing your sample. And modulus, through using that deformation mode, is shown by E. And on the right-hand side, it's shear modulus. So it deforms your sample in another way and direction, and it's more assigned to rigidity of your material. And the way that we show shear modulus is with a G, since it's a different deformation mode. So we use different letters to show that. So just to wrap up all the points that we talked about. So far we talked about modulus. Modulus, it's a material's overall resistance to deformation. It has elastic components and viscous components. Elastic or storage modulus expresses the ability to store the energy, or if you remember exactly the height, that ball can go and bounce back up. And so basically it stores the energy, the potential energy that it previously had while you were holding the ball from a certain height. And then the right-hand side, you see a viscous component, or it expresses the ability to dissipate energy through heat, through the matrix of your material. Storage modulus is shown by E prime or G prime, and viscous modulus or loss modulus is shown by E double prime or G double prime. So I want to take a moment and talk about tan delta or loss factor, which is very important. It has many applications. Many folks and scientists are looking to have a very good understanding of the tan delta of the samples for different applications. We're going to see, we're going to go through one of them today, but let's just understand first what we're dealing with. What is tan delta? So simply the tan delta is the ratio of loss modulus over storage modulus. So the component of your material that dissipates energy through its matrix over the component of your material that can store the energy, or is responsible for elasticity, the tendency of your material to going back to its original shape. So this ratio is called loss factor or tan delta, and it is measured for ability of your material to dampen noise, vibration, and different sound or different waves. And it is very important to understand that, and it's being used for different application. And the other important part is that this ratio is very sensitive to changes. So by measuring that, it can obtain very accurate results. So, but let's look at a typical graph of the DMA results. So as we mentioned before, based on the frequency you're applying your deformation or force for your material, the material behavior will change, as well as temperature has the same effect on your material. So by changing the temperature, your material will show different viscoelastic properties. So it's important to take note that frequency and temperature can affect your material's behavior. So starting from lower temperature, for viscoelastic materials, let's say a polymer, you'll have a glassy region, which your material is very hard and they're like a rigid, solid material. And as you increase temperature, you enter the glassy state or the transition region that your material gains more energy, and let's say again the polymer, so the polymer chains gain more energy and mobility, so your materials become softer and it has the capacity to move around more, but still in the solid form. So you can see the storage modulus, or the amount of energy you can store in your material will drop, and the reason for that is that now your material has gained mobility. So by applying any source of force or deformation, it has the capacity and capability to dissipate that energy. And after that, we have a rubbery plateau by increasing temperature in storage modulus. And after that, as you increase the temperature, you go through the melting point, and basically you have a very huge drop in storage modulus, and your material becomes more of a liquid. And more than the typical temperature profile of your material, when you're at lower temperatures below the glass transition temperature or the glassy state, the part that I mentioned, your material gains more mobility. You'll have three different stages of different changes in your material. For example, so there is alpha temperature for a transition, which is glass transition. And before that, we have three different temperatures. Beta is the temperature that the side chain of the molecules are moving. And this is a very neat application of DMA, that actually there is an instrument that can pick up those changes and phenomena happening in your material. And for the other regions, you have stretch and bending or local motions of your molecules. And so the advantage with DMA is that it's sensitive enough to pick up those changes. As a comparison, for example, DSC is not capable of picking up those points. So moving forward, let's go through a case study and see how we use really DMA and all the theory that we've been learning so far. So this paper title is Toward the Manufacturing of a Non-Toxic High-Performance Bio-Based Epoxy and Fiber Composites. So basically the whole goal behind the study was to manufacture a environmentally friendly composite using a natural fiber. And so the instrument that was used for this test and this research work was DMA plus 300. The test was temperature sweep. The temperature was from 25 to 165 degrees Celsius with a heating rate of 4.8 degree per minute, and excitation mode was tension. So exactly the same deformation as you can see in the previous slides in the image, and the frequency that was used from 1 to 4 hertz. The static displacement was applied and a dynamic displacement of 10 micrometer. So the goal was to evaluate the effect of natural fiber in reinforcing an epoxy composite. But let's see what are the results. So as you can see on the left-hand side, you have tan delta. The ratio of loss modulus over storage modulus that we mentioned is very important, very sensitive. And then the right-hand side, you can see the loss modulus. Let's start with the left-hand side. So the tan delta, it is well known that by starting from certain temperature and having a temperature sweep test, as you increase the temperature, you should see the glass transition temperature as a peak in that tan delta graph, as can be seen on the left-hand side. So the tan delta, the height of the peak, can be different based on how capable of your material is in dampening. And as you can see, for example, for sample series C, the height of tan delta is lower, and for the composites, for the pristine epoxy, the height of tan delta is higher, which means it can dampen vibration better and with a higher capability in dampening. And so a very good point to learn from this graph is that by increasing the frequency of deformation, your tan delta peak will shift to the right-hand side or higher temperature, which means your material starts behaving as a softer material later at higher temperature, which means your material stays stiffer at the temperature below. So the higher the glass transition temperature, the stiffer your material before that temperature. And so as you can see, that glass transition temperature has shifted higher, so your materials shows stiffer properties. But in reality, we know that because we're applying the higher frequency, the natural tendency of your material is to behave like a stiffer material. So that's the reason why your material behaves like the glass transition is happening at a higher temperature, or why your material is behaving as a stiffer material, because the way that you're applying the force doesn't give enough time for the material to relax, and it behaves like a stiffer material. On the right-hand side, we see the loss modulus, or the ability of your material to dissipate energy through its matrix. And as can be seen, so that's the soft components of your material, and that's the part of your material that wants to dissipate energy and not returning that energy. And as you can see, by increasing the temperature, it clearly shows the material becoming softer by going through a peak. And you might be asking, what is the difference between these two peaks? But as I mentioned before, tan delta is the most accurate way to measure that glass transition temperature, because it's the most sensitive parameter that you can obtain from your measurement. So next slide is the storage modulus of the same sample. And again, different frequencies. And as you can see, by increasing the temperature, the material is going through the glass transition. So now the storage modulus, or the stiff part of your material, or the part of material that returns the energy that you already applied to your material, is dropping because your material is becoming softer. So another application for DMA tests is evaluation of rubber tire performance in rubber industries. And so again, let's talk about tan delta. So for different temperature and evaluation of the rubber behavior, for example, let's say tires, at different temperature, you're looking for different tan delta. I'm going to explain why that's needed. For example, let's say ice traction. So at lower temperature, like -10, you want to have a tan delta peak, which is higher in terms of height of the peak, because you want to make that traction with the ice. And for 0 degree, we have wet traction. You still want it to be high tan delta, so the damping performance should be high. But at higher temperature, like 30 degrees C, the traction changes to a rolling resistance. So in a simple term, what happens is that it makes a barrier for your tire to roll properly by having a high tan delta. So you need to consume more energy, more fuel for your car to have that rotation in your tire and move eventually. So you need, for that specific temperature, you need low tan delta because you want to reduce the rolling resistance. So that's an example of tan delta scan for, that's again, temperature suite for different samples of rubber material. So with different chemical formulation. So on the blue side, blend A, as you can see, shows a higher heightened tan delta peak. And blend B in orange line shows a lower tan delta peak. So as I mentioned before, for a higher temperature, you want a low rolling resistance, or a low tan delta, the low height of the tan delta. So probably the blend B will be a better choice for all season tires. However, for winter tires, blend A would probably be a better choice since it has higher tan delta peak. So conclusion of this webinar, we went through some theory of viscoelastic properties of the material and how dynamic mechanical analysis works. And we learned that DMA is a powerful tool to measure the viscoelastic properties of the material in different range of materials, including filled and unfilled polymers, rubbers, and soft materials. DMA is a non-destructive test, and unlike static tests, a dynamic periodic load is applied, where a constant load, in comparison with the static test, the constant load is applied. That's all for today's webinar. Thank you so much, everyone, for joining us. Arya, I'll let you go through.
Perfect. Yeah. Thank you. Thank you, Arya, for that. Yeah, folks, so we're about ready to close up the session. Just a little outro here to wrap things up. And then again, we will be going into the formal Q&A here shortly. So just a few closing notes here. Again, this webinar will be available for playback. We do have a library of previous webinars available on our website, as well as tech libraries, which features some of the various publications that were presented here today, amongst others related to various techniques. So definitely feel free to take a look. A lot of good resources there to make use of. If you're not already doing so, give us a follow on LinkedIn. This is where we will be posting, upcoming webinars, new events, blog posts, things of this sort. So if you are interested in keeping up to date, definitely feel free to give us a follow there. I will also just plug a few upcoming webinars over the next few weeks. So next week, this time, we will be doing a special guest speaker, Jonathan Martins from ARDL, will be joining us to look at optimizing test parameters for filled and unfilled compounds. Again, focusing on DMA. So this will be another DMA focused webinar. About midway through November, we'll be doing a thermal conductivity measurement theory and applications. So kind of a similar idea, looking at some background information on various thermal conductivity methods as it relates to some of the C-Therm product line. So that'll be on November 12th. And then the following week, we'll be doing a TMA focused theory and applications webinar, again, along the same vein, but focusing in on the Rigaku product line. So if those are of interest, definitely feel free to sign up. Those are available and open for registration right now. We'll also be traveling here, some folks visiting a few conferences. If you're in the area, definitely love to connect if you're free to do so. The International Thermal Conductivity Conference held in Charlottesville, October 27th to 30th. We'll have a booth number 6. If you're in the area, definitely feel free to stop by. And also a little bit later in November at the Polymer Testing World Expo North America, which is being held in Cleveland, Ohio. Again, we also have a booth there. So we'll, if you're in the area, planning to stop by, if you're interested in connecting with us, definitely do so. All right, so that brings us to the end of today's formalized session. At this point, we'll go ahead and stop the recording. So for those who are still on the line and would like to join for the Q&A, please feel free to stick around and we'll jump into that side of things.